Welcome to Unscripted with Jeff Pedowitz. I sit down with remarkable people from very different worlds, security and science, business and medicine, technology and the arts, for honest conversations about AI and where it's taking us. No scripts, no talking points, just what they actually think. I'm Jeff Pedowitz. Let's get into it.
Everyone's suddenly promising humanoid robots in every home and factory. My guest today has spent 40 years on the part that actually turns out to be hard. Klas Nilsson built one of the first digital robot motion-controlled systems back in the 1980s at ABB, became a robotics professor in Sweden, and founded a company called Cognibotics to solve a strange problem. Despite all the hype, less than 1% of the world's work is actually done by robots. I'll tell you why, and why the answer isn't a smarter chatbot. So, I wanted the honest view from someone who makes machines move in the real world. What's real about the robot revolution and what's science fiction? Klas, welcome to Unscripted. Let's get into it.
Thank you for having me here.
Absolutely. So I'm curious, how did you get into robotics in the first place?
I really want robots to help humans. And that started already when I was a kid, because I'm grown up with farming and I hated it. I wanted to read books and compute things and things like that. But I had to do this hard labor work. And at the same time, of course, there are machineries. And my father also enhanced some machines and even built some machine like a forestry machine. So I learned early that, okay, building machines that make the work easier, that's a good thing. And then when I was a little bit older, after around 16 or so, I'm old, when I encountered computers and programming, then it got obvious to me that you combine the machine and the computer, and then you get a new type of machine that is not predetermined what it should do. And that's the robot, simply. The mechanized worker, that it can be configured and programmed according to customer needs.
Well, farming is definitely hard work. So now, 40 years later, are there robots helping farmers make it easier?
Yes, there are. I mean, there are milking robots. There are robots moving on farmland, although the farmland needs to be a bit prepared. So yes, there are those cases. But it's a little bit of preparation with the environment. I realized that the most critical area for good robots is actually in manufacturing. Of course, everyone can dream about your home robot that does the cleaning and everything you don't want to do yourself. But that's a very, very hard problem for reasons we might get into here. But in manufacturing, you both have quality needs, you have the productivity needs that requires performance, reasonable cost, but maybe not going for the very lowest cost, and so forth. And I often worked in factories during summers as pupil and student. So I could see that there was a lot of manual labor that was almost like farm work. It's not for humans. And nowadays, when you have shopping on internet and the logistic centers and all that handling, it's the same there. I mean, there are so many tasks that humans shouldn't do.
Well, we're starting to see robots now in the supermarkets. They're coming up to greet you, or they can help you find items. So they're kind of like attendants
Yes,
in the aisles.
but they don't pick the items and put it in your basket, because it.
No, not yet, but I imagine hopefully that's coming soon, because I hate grocery shopping.
Yes. So
one of my favorite. Go ahead.
Yeah.
Sorry.
So I also decided to work on the arms, the hand, the manipulations, grippers, etc., and not the mobility, because most, or at least a lot of researchers and developers in robotics has focused so much on mobility, wheeled, later legged, and of course that's important, but so many are doing it, and rather well, I would say. And then we have the issue of hands. Hands are extremely difficult. But in manufacturing, you can have, just like you work with handheld tools, and you can have end effectors to robots, and then you have the remaining problem. Okay, how is the task explained? How does the robot understand it? How can it perform? How does it adapt when things are changing? Because of course, if it's the same motion all the time, that has been solved for 50 years. But what happens when things change, and how does the robot adapt, and how is it easy to teach it, and so forth. So that's my focus.
What makes the hand so much more difficult? Is it all the dexterity and the various different movements?
Yes, there are both lots of degrees of freedom, and the human hand has a quite high strength compared to the weight of it. And if you look at hands today, I mean, you have both in China and US and elsewhere. I was at Automate in Chicago a few weeks ago, and I noticed that the Chinese hands there, they were more favoring of having motor drives directly in the fingers. So they actually managed to miniaturize it so well. Whereas others, including Tesla, I think, for the Tesla bot, has been trying to have tendon-driven fingers, but many practical problems there, and I don't see that any of those as unique or the only solution will solve the problem, because there are, for instance, if you look at the human hand, if you move fast and you hit something, when you move fast you are more relaxed in your muscles, and if you bounce into something you're not hurt really, not like a humanoid hand that hits into something. And then of course you could say, okay, you can have a few fingers as a spare and the robot might be able to replace them by itself. But well, if you have tendons, that's difficult. If you have the direct drives, you always a cable, etc. So I don't see any of the existing hand solutions as really promising for the future. So I think Boston Dynamics is doing the right thing when they say, okay, let's just go for a simpler hand for now, and then better hands for the future. That's the big research topic.
So, what would need to happen from a technology standpoint to produce a robotic hand that's on par with a humanoid hand?
Okay, if we just continue on the hardware side, because then of course you have the software, and how do you plan and command all these degrees of freedom. But if we just look at the hardware, what type of gears and actuation should you use? I think we need a mix of direct uh, transmissions in some degrees of freedom, such as for the entire finger, whereas you can also have some tendon-driven motions, maybe outside the in let's see here, maybe to control the degrees of freedom in each finger. But the variable stiffness problem is still unsolved. So if the variable stiffness should be by means of hardware, it's still unsolved. And then you have all the material problems. It's still rather heavy and clumsy with the metal. And how do we use composites, carbon fiber mixed with other materials and so forth? So hand research is very difficult, and I'm unfortunately a bit too old to get into that field.
It's still exciting nonetheless. I had a manufacturing client a few years ago, still one of my favorites. And you talk about robotics and manufacturing, and they were frozen peas, and so they had thousands of these peas going along the conveyor belt, and they had a laser that was aimed at the belt, and if the pea was a micron too big or too small, a pocket of air would push the pea off the belt into a rejection bin.
Mm.
I just thought this was the coolest thing, I gotta watch it for an hour, just these peas coming back and forth. So there are many applications, right? I mean, and that was probably more just standard manufacturing than robotics, but it's easy to see the potential, when you're doing all these variety of tasks, especially at high volume, where robotics could play a vital role alongside humans.
Yes, absolutely. And I mean, we have had robots for a number of decades now, and every car is, at least to a large extent, built by a robot. So that's fine. But still, there are so many remaining problems in just making, let's say you have normal end effectors, grippers, cutters, drilling tools, etc. But still, how do you explain the task for the robot? How can you be sure that the interpretation of the task is correct all the time, such that you can let it run in production? How can the robot work beside humans? I mean, if you look at the standards for functional safety in industry today, the notion of a cobot to work next to a human, yes, it can, but not with full productivity, with the full speed. And even if you look at the humanoids today, they are rather heavy and clumsy and too much metal moving around. So for robots to work productively near humans, there are so many both hardware and software problems still to be solved. But we are working on them. I mean, different researchers take different parts, and at Cognibotics, we decided to start with some of the fundamental issues like accuracy and motion speed for lightweight structures, where we have really, really exciting results.
So, you've been doing this for a long time. Is there a belief about your field that you recently changed your mind about?
Yes. Since the LLMs came, we have, of course, all been thinking about, okay, what does this mean for also robot motions? And we have, for instance, the visual language action models, where the actions are represented by action tokens. But teaching and having a robot to learn the task, it requires quite a lot of training. And yeah, okay, many are working on that. But I could never see how that could really be applied on the factory floor, because one thing is a robot that does something that is approximately right or inspires you to use it further or so. That's a big difference from that to a robot that actually performs work reliably in manufacturing. And there are so many examples when robot designers have thought that, well, we shouldn't complicate things with this hands-on touch-up of positions and adjustments of text programs, and let's get rid of all the complexity. And that's what you do when you have this AI-driven robots. But in the end, when you are on the factory floor and something happens, it could be just some slight change that you don't want to start a retraining project because of that. And just a simple update from learning, yeah, okay, maybe, but you want the worker to have an interface wherein he or she can influence the motion. Not redefine it totally, but just adjust it a little bit. And I didn't understand how the action tokens that live in their world could really be coexisting with a worker's abilities to understand what the robot is doing and adjust motions. But then I have understood that if we keep the LLMs on a task definition level, and we let the action tokens work on in a synthetic world where it's not even the digital twin of the robot. We call it the digital cousin because it behaves differently. For instance, when humans talk about force, let's say the robot should push in a bushing in a hole or assemble something with a certain force, or you should polish something with a certain surface force. What people mean with force and what is reflected in LLMs today is different from the force you need to deal with down in the servo control system. So it's better to keep the human notions on the synthetic world level, where it's also the open world assumption. And then we can have an intermediate level where digital twins, existing software tools in industry, for machine programming, control, monitoring, supervision, and all of these things that are there, and you don't replace all of that immediately. And there the digital twin can be. And then we have the robots that we can then call a physical twin, because as you might know, we also work with calibration a lot, and that is not only to make the digital twin resemble the physical world, but also update the physical world so it agrees more to the digital one. But those two things are on a lower level, and we have to separate that and use that without LLMs, and then keep the LLMs on the open synthetic world above it. And then, of course, there is a challenge how to link these two, and that's also what we work on at Cognibotics. We have a concept we call motion intelligence, how to do that lower thinking.
So does the LLM model become the main operating model framework for the robot, or is there a separate operating system that runs the robot?
Yeah, so this means that LLMs are more on human interaction level for defining and redefining and adjusting tasks, and also setups and configurations, whereas on the motion level, something different is needed. And so language
How do you,
is then human language is on the upper level, and then on the lower you need another language, and that is also why we have developed Juliet as a Julia-based language, because there is a need for real-time textual language that has meta programming fundamentally built in an efficient way.
how do you decide from an autonomy perspective when should the robot take control? When should the human take control?
Yeah, that's a good question. I mean, there has to be an interplay between all these levels, and sometimes you actually need to connect them. Let's say you work with the task definition and you want to haptically control a robot just to get some force data to further refine the task. So yeah, it's a good question, and a lot of work in this area is really needed.
So with, I mean, there are a lot of robots, and we've had them for decades, but still only about 1% of the total work worldwide is done by robots. But why is that?
So I mentioned hardware, and there things are moving forward. On the industrial side, at Cognibotics, we have two special robots for cases where robots weren't capable. That's why we have invented one type of wrist and one type of elbow. But that's kind of still niche applications. We have lots and lots of very useful hardware. So I should not blame hardware in general for manufacturing. We have lots of solutions. Then to define and tell the robot what to do and have the robot working with some kind of awareness of uncertainties. And what happens when the real world is not agreeing with the imagined digital world? And in some areas, like in handling, in intralogistics, for instance, it's not about full accuracy. And if some packages are not placed properly, it's okay as long as it can be detected. So that's kind of an area where today's hardware is basically fully okay. But then when we go to tasks in general, including orientation control, because it's a 6-dimensional problem. People think that, okay, we are in our 3D world, it's X, Y, Z, but it's also tool orientations around those axes, so it's 6-dimensional. And then a thing like representation of the tool or pose, uncertainty is even mathematically not handled correctly. So that's where we work to build the foundation of the control layer, ranging from individual joint controls and up to the task control, including uncertainties, but also force. That's a key thing with robots in industry today. They are almost only programmed with respect to position orientation, not with forces and torques on the tool. Of course, if you have a robot that does polishing, you might program it by putting a position path a little bit below the surface and then make the arm a little bit compliant of the tool. And then you get the force. But the robot has never been informed about what forces is it actually supposed to exert. And
how much is too much?
and as soon as all such knowledge stays in the head of the humans that teach the robots, what can the robots do? Of course they are stupid. That's why we need to equip the robots also on lower level with much more expressive tools. How do we express force? How do we express the uncertainty of it? And how do we define the monitoring in an easy way? So there are so many of these controlled problems in manufacturing that you need to solve them before making good humanoids also. And that's why I focus on manufacturing, actually.
Well, it is. I remember when I was first learning how to code, and one of the first days, and our professor said, "Okay, look, tell me how to turn around, walk to the door, and open it."
Yeah.
And so, and so we're like, "Okay, turn around," and he would just keep turning around, until we realized, oh, turn 180 degrees, right? Oh, walk 10 paces, raise your right arm 45 degrees, turn the knob, 45 degrees clockwise. So you realize that it's not just a simple matter of, humans can absorb things in multiple layers simultaneously because we have our vision, right? Our ears, we have all these different senses we can learn. It's robots need much more intricate instructions to be able to function.
Yes. And that's a good example that on a high level, the system needs to understand the task, the goal of it, the variations, and so forth. And there, LLMs and other techniques are perfectly fine. And then that has to work together with industrially required features, such as how can you assure it, how is it functional, safe, and how is the monitoring done, and so forth, and how can some production technician adjust the task slightly or a lot if that's needed. So yeah.
So robotics has been around for a while, and then every few years, right, somebody makes a big proclamation that the humanoid robot revolution has arrived. You've been through a few of these. What makes this wave different, if at all?
It's of course the AI developments with LLMs, etc., but it's not sufficient. Then we have all the hardware developments ranging from motors, gear reducers, joints, bearings, different materials. That's also enable a lot of things, but it's still not sufficient. So I foresee, call it another AI winter coming. It will only be a mild one this time. The AI has been going up and down, and we call the down periods winters.
Yep.
And I think there is a need for one more winter before the community as a whole has learned sufficiently many of the lessons. What's hard? Why? What needs to be done? How do we build systems? Because for instance, in academia, it's based on that you specialize and you can publish in a certain field. When you build products, then you have to build systems and teams around that and think differently. On the other hand, if product development so far has been too limited regarding the fundamental limitations, because if you just see a market and you go for that, okay, that's one thing. So in that sense, the current humanoid developments are really, really what we need, because it's to a large extent commercial, maybe too big promises, but nevertheless commercial. And it at the same time goes to fundamental issues. And that's why some solutions will come up, but we will also learn more about the limitations. And since many experts and users work together or on the same type of system, so to say, it will also be like an forum where they meet. And that's the nice thing with robots in general and humanoids in particular, that all the competencies that can come together, try to solve a problem and learn not only in your own area, but you also learn a lot from the others. So I think the developments going on right now, they are necessary for disciplines to get together, and we have lessons to be learned. And of course, there will be some applications that are successful, but I think it will take over 5 years, maybe more, 7, 8, maybe 10 years until we see the real breakthroughs in more general purpose humanoid robots. But in the meantime, we will have more and more solutions that can work in a manufacturing and production environment. And you see already existing humanoids. I mean, in car factories, they can have a role. Hyundai and Toyota, they can find spaces. But what does it take to make these robots useful in a small or medium-sized company, where they don't have this type of volume production? That's where I mean it will take more than 5 years additionally until we are there. We are.
Yeah, I'm even thinking just something simpler like our televisions, right? That they were talking about high def and big screen televisions back in the early 90s. And back then, you were ecstatic if you had a 25-inch screen. Like that was like you were living large, if you get to have a TV. But it still took, about 15, 20 years before the TVs really started becoming big and light without losing any of the functionality or the picture. And now, obviously, that's a very different engineering problem than robots, but principles still, right? How do you make something highly functional, light, versatile, cost effective? Because those first televisions were so expensive, to get a big screen TV, you were spending $4,000 or $5,000. Now, of course, you can get one. So you said about 10 years. Is that how long it will be before we can expect to see humanoid robots in our house, or will it be longer?
It will be even longer for a common man, so to say. But in 10 years, I think some will have, and maybe even just 7, 8 years, some maybe wealthy persons that want the latest gadgets will have them, and they can do something useful. Yes, absolutely.
So, right now, you're not the only one doing this. There are big companies that are pouring billions of dollars into humanoid robots. But you're developing your own language and your own hardware. Why won't the big guys just win on scale alone?
Why they wouldn't scale? Can you repeat?
Well, they are putting billions of dollars in investment into this, and you are also investing, but you're taking a more nuanced and disciplined approach with how you're approaching the language for the robots and the hardware. Why do you think the big guys will run into challenges despite their incredible resources they have?
Very few persons have understood all the problems. Take NVIDIA, it's so famous, but if you look at their models, they don't really take force and elasticity and physics as the primary. They go from geometry, and they are super scalable, and you can do very nice things in the synthetic world. But if you go down to more craftsman-like emotions and learning from physics, people believing that they have the solution, they will learn that, okay, there is more to it. So, and that's what I also meant with that, the lessons to be learned is that, okay, what you saw as the solution has its limits, and where are the limitations? What do we need to combine it with? And I hope that some of the work we do at Cognibotics, I mean, we are scaling up carefully, more European style, not just throwing big money into something like in US and China. So we look at the fundamentals, but I hope that within a year or two we can start meeting more of the other stakeholders that maybe have bigger resources and can build on some of the things we are doing. Because in the end,
So, I
sorry,
mean,
because in the end we
yeah, go
have
ahead,
we
Klas.
have the common goal that robots should help humans, so humans should only do human-friendly work.
So, if they are so helpful and they've been helpful, why do you think, going back to that 1%, why is adoption still low? Is it the limits of the technology itself? Is it the promise of it? Is it just human behavior?
Yeah, it's the technology itself. It's not scalable, easy to use enough, and it ranges from hardware that is still too heavy and clumsy and cannot be made safe when it moves fast enough, to the software. How do you redefine tasks? How do you influence the robot's behavior? How do you certify its safety? And it's such a long list of problems. We can't go through it here, but it's technical problems, but also technical problems that has to do with human perception, human cognition. I mean, there has to be a dialogue between the human and the robot, and that there are still lots of challenges in that area. So the barriers are mainly technical, but the more of them we overcome, the more we can work with the human robot interaction and common understanding and safety and those type of things. And I'm really, really optimistic about the future, because all this means also that, like, skilled touch labor will become valuable also as robot teachers. I mean, it's so much talked about today that AI takes away a lot of job. For it could be for graphic designers, it could be for lawyers or legal department workers. Yes, many of those works may disappear, but the future robots will allow a worker or a craftsman to teach motions, not only by telling, but haptically or by force, showing, holding in the hand, and work with the robot. So no matter if you are a carpenter or a bricklayer or what, you should have the robot as your friend and a slave that you can teach. And why not sell your services that you have been teaching the robot as as a worker, so to say. So I think in total, robotics and AI will create new jobs. It will take away some, and it will create new markets. And I really look forward to living in that future.
But so related to AI though, and putting it into physical robots, what do you think people are getting wrong right now?
That they are to think that LLMs are intelligent when it's just a predictor. That's one of the things people get wrong. And also the actual complexity and behavior of humans. Humans don't understand themselves, and AI can help. AI can help humans understanding themselves. For instance, how does a psychopath behave? If a robot is made very, very understanding and clever and helpful, etc., it will still be like a psychopath. And realizing that the robot has no empathy. Of course, you can program something you call empathy, but it's not a biological intelligence that represents empathy. So in the end, this will help humans to understand what is really human values. How do we interact? And this is also why robots will stay as the second class individuals, and they should be machines. They are machines. No matter if they have awareness or consciousness, it doesn't matter. They are machines to help us. And that's how it will remain in my lifetime. Of course, I cannot say what's up in 100 years, but for the next decades, I think that will hold.
So you're building this in Sweden, and both us here in the States as well as China, we're having this arms race on humanoids. Does Europe have a different or better idea about robotics, or do you think Europe's getting left behind?
No, I don't think Europe is left behind. Well, it is from an investor point of view currently. And that is what is the big difference between Europe and US. And I think also Jeff Bezos said that that is the only difference between US and America, that you have such investor willingness to take risks and you do big things, whereas in Europe we are fragmented with different languages and cultures, etc. But I think in a few years, because we have a good education system, so far many European experts have moved to US and made their career there, and other technologies are simply bought. But I think the world will be kind of multipolar in the technical sense, and there will be an exchange. And since European education and fundamental research and innovation capability is rather good, I think Europe will be rather well off, maybe even the best well off. We will see what happens with currencies and autocratic regimes, etc. So I'm in general very positive to how the European future looks.
Maybe England could use a robot for prime minister, since they can't seem to get one right.
Yeah, well, we will get the new one a chance now and see what happens. No, humans should do human things, and robots should be doing the boring things.
10 years out, do you think robots are everywhere, or are we still saying any day now?
10 years is a good period, so we will see many, many more robots in service professions, in manufacturing, maybe not so much domestically, but it will come step by step, and handling applications, maybe some craftsman applications. But we have to work on the fundamental barriers and solve those, and then how the commercial ecosystem will look for that, that's still unclear. Because sometimes, even if you have the right technology, if you can't earn money on it, it's a problem.
That's true. Are you worried that the investment in AI, and AI-related software will dwarf investment that goes into robotics?
If I'm worried that the investments aren't going into the right areas, you mean?
Yes.
Yeah. Yes, definitely. Absolutely. It's a pity that so much investment goes into things that cannot work. I mean, it's impossible that these commercial or technical outcomes will be reality. So that's why I hope that in not too many years that there will be some more real lessons learned. So investments can go more into the things that can actually make a change and actually work in practice. And that it's not only how things look at YouTube, but how it works in a factory, how it works in a logistics center, etc. That much more of the real work environment will be shown and analyzed, so forth. So we are still in the hype phase. I look forward to within 2 years to get into the realism phase, and then from there we can start to build the real things again.
Boy, that Gartner model really holds up well over
Yes.
time. Yeah, the hype cycle, the
Yes.
trough of disillusionment, and that works for just about everything.
Yeah.
Yeah. So what are you paying attention to right now that most people aren't yet?
I would say semantic gaps in systems. Because one of the misconceptions is that, okay, you have the machine, the robot, it has its properties, its language, its motion, its server, lots of these things. And then you have the tasks that you want to have done. And the system is then, I mean, you have the user level things, so the user programs in either some just visual way or a textual language or some way, but it's the user space. And then in the system, there are, of course, engineers that have engineered lots of things, motion control and safety functions, etc. But the problem is that these two parts cannot really be kept separate all the time. Because let's say you encounter applications where the robot is not capable enough. Yeah, then you have another requirement, and then you look at the design of the system. And you need to have the system built in a way that connects to the user space. And it's also for understanding when things don't work and for monitoring. And that's why also at Cognibotics, we started with the calibration. Because it's not only that it's handy to have accurate robots, it's because if there are inaccuracies that create confusion for the user, you need to be an expert to understand how you need to program. Instead, if you make the robot calibrated and accurate, and then we have other algorithms that deal with the resonances, for instance, then the system gets easier to understand. And then about semantic gaps, we need to build all this such that if something inside the system, let's say you pick and place something, and then you place something that should be assembled. And as a human, you might shake a little bit to get things in place. How do you do that in the task description? Well, maybe you can't. So you need to be able to move functionality from the system to the user and from the user ideas back into the system. And also inside the system, the servo and control level is different from the language interpretation trajectory generation level. But also there, we need to avoid semantic gaps, which means that the meaning of things in the different parts of the system needs to be coherent. Of course, you will always have some special software like a physics engine that's programmed in whatever way. But the way we build the systems needs to be done with far less semantic gaps than we have today. So motion interface, process interfaces, I/O, interaction devices, how a user talks about the intended task, or if there is a problem in the task. All of these things have to be built on a fundamental layer or fundamental technologies that avoid semantic gaps. And our conclusion is to build this Julia based, because Julia is not just a programming language from MIT, it's also a language that has meta programming built into it in a certain way and has a runtime model that enables full efficiency. And it's not object oriented, because object orientation works only in declarative languages. So Julia made these things the right way, and that is what we are building on when we build the system also. This is, of course, very abstract, but just to give you a little bit of explanation of what I'm paying attention to now.
It's a lot of good work. So if you had the chance to go back and visit your 10-year-old self on the farm, what would you say to him?
Keep on working, do the math, think freely, just work on, and the future should be bright.
Great words. Klas, thank you so much for being on Unscripted.
Thank you very much for having me here. Very interesting. Thank you.
You got it. We'll look forward to more great things from you.